This video will demonstrate the new compression feature available with Storage Foundation 6.0. We will be using a canned script for our demonstration, but it is running real commands on the back end, which we will point out as we go along. In part 1, we are going to show compression with a single file. Later on, in part 2 of the demo, we will show compression of a directory. To begin with, we will create a new file system for this demo. You can see from the output in our makefs command it has layout version 9, which is the default. After creating the file system, we are going to mount it. Notice that there are no additional options needed when we are mounting the file system for use with compression. Next, we are going to cd into the mounted file system and make a 5 megabyte text file. We are creating a text file as our example, partially because they are great for compression. When this is done, we will make several copies of the termcap file into the 5 megabyte file we just created and call it big file. When this is complete, we will save a copy of the file so that later we can do some comparisons to the compressed file. Here is the file before compression. We will run the command ls-ls against our 5 megabyte file. In looking at the output on the left is the number of blocks, 5518. In the middle is the size of the file, which is 5 megabytes, or 5649,721. Next, we will compress the file with the command vxcompress filename. After compression, we will run the ls-ls command again on the file and see that our number of blocks has been reduced to 1797 blocks, but the size of the file remains the same, 5 megabytes. We reduce the space in the file, but the data remains the same and is still accessible. vxcompress has the ability to look at a file and tell you if it is compressed or not. In running the vxcompress-l filename command, we can see quite a bit of information. When we compressed big file, we reduce the space used with this file by 68%. We have 1789 physical blocks currently being used. If we expand this file, we would go back to the original size of 5518 blocks. The next column of %extents, which has a value of 100%, is the percentage of extents that are currently compressed. Currently it is 100% because we just compressed the file. If in the future we had writes to this file, this percentage would go down. It also gives us a way to look at the file and see if we need to compress it again. Within 6.0, we have a single algorithm for compression, but in the future we are planning on offering multiple algorithms. gzip is the name of the algorithm that we are using right now. Along with that, we have a strength rating from 0 through 8 that defines the value which represents a trade-off between CPU time and effectiveness of the compression. 0 gives you the lowest compression, least amount of CPU impact, and the highest throughput speed. 9 gives you the highest possible compression with the highest CPU usage and takes the most amount of time. 5 is the default value and the most common trade-off of CPU, speed, and space savings. We can also run fsmap on this file, with the option P, which shows the differences in the chunks of data. With the big file, we have it separated into 6 chunks, with the logical sizes being much larger, based on the compression when compared to what is being stored in the physical size. From here, we can check on the compression of the entire file system. By running fsadm-s compressed mount point, we can see the compression stats on the file system. From here, you can see that the entire file system is 3% compressed. The compression on a single file is much larger than that, but this utility also counts the metadata based on how we have the file system set up. There is quite a bit of metadata that is not being compressed. We will see an example later with the actual compression much larger. We can also read a compressed file. In our example, we will run the head command to see the first 10 lines in the file. As you can see, it looks just like the termcap file even though it is compressed. We can compare the compressed file against the backup of the file we took before we began compression, and there is no output because there is no difference between the two files. The two files are exactly the same in terms of content. The only time that big file would be uncompressed is when we write to the file. To show this, we are going to write in the middle of the file using the dd command. We are going to write a block from termcap 50 blocks in with a 64K block size to update somewhere in the middle of this file. Checking the file again with the vxcompress-l command, we will see that the compressed extents have gone down from 100 to 83, and that the compression percentage has gone down from 68 to 55% for the file, because we overwrote some of the data, causing it to be uncompressed. If we also look at the file with the fsmap command, we can see that the chunk of data with the dash in the physical size is the uncompressed data. So with the update, we no longer have the old data. If we once again compare the current versus the saved copy of the data, we see a difference in the data. We could recompress the same file, which customers can do when they update the data over time, but for our example, we will uncompress the file using the vxcompress-u command. Now the file is back to normal. The ls-ls command shows the file is the same as it was originally, containing 5518 blocks of data. With the fsmap, we see two chunks of data with the physical size showing the dash, which means the physical and the logical are the same. Now we are going to clean up and move on to part 2, which is compression of a directory. For our demo, we did a wget of the Symantec.com web files and tarred them up so we can show the compression. So here are the tar files obtained with the wget command, which resulted in approximately 231 megabytes. I'm going to untar the files into the demo file system. You will see quite a few website files pass across the screen. If you could not read them all going by, I will tell you that most were HTML or JSP, which is a fairly compressible set of data. There are not a lot of video files in the tar files. So if we look at the compression of the file system using FSADM, we see that we are currently at 0% compressed, which is what you would expect being that nothing is compressed yet. At this point, we will compress the directory. It will take about 10 or 15 seconds to do this. The process is multi-threaded and will crawl through the directory compressing files. What we are looking at now is the vxcompress-l output from each file compressed. If you look at the files, they are all relatively small files that are compressed around 80%. When we look at the file system using FSADM, we see that the file system is at 53% compressed. This is much higher than the 3% we noticed earlier when we compressed a single file. And so we have reached the end of the demo. Thank you very much for your time and attention.